Hey, now that we've actually gone through and we've solved some basic velocity, basic acceleration equations, we got an idea what's going on with motion. We're able to graph it out, and we're able to maybe even describe it and talk about it. Let's go into problems that aren't necessarily as basic. In other words, they're a mixture of displacement and time and acceleration. So these are all problems that involve acceleration at all times. If you ever have a constant velocity, you only use the constant velocity equation, not these acceleration equations, and vice versa. If it has an acceleration, you are not allowed at any point in time to use the constant velocity equation. So make sure you don't mix in constant velocity into acceleration problems. Now, these equations up here at the top, these three are called the kinematic equations. Now, they're written in, if you will, IB form for you because that's kind of the direction that you're going. And they each are missing a critical thing, and they're derived from the basic velocity and acceleration equations. And never mind that. I'm not going to go through the derivations for you. This equation, final velocity equals initial velocity plus acceleration times time. Notice that it is missing displacement. There is no S in it for displacement. So if you have a problem and you don't know anything about displacement, but you know three of the other four variables, you're looking for the fourth, that would be the equation to use. Over here, displacement equals initial velocity times time plus 1/2 times acceleration times time squared. That, in the long run, I'm just going to go ahead and tell you, that's going to end up becoming a favorite over time. And then this other one over here is also a favorite. So this one doesn't have any final velocity. This one's nice because it doesn't have time in it. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. It might be good, guys, to go ahead and start building yourselves an equation sheet in your own notebook. We're going to give out to you a master equation sheet, but that's going to, I don't want to give that out to you just yet. So it might be good to go ahead and start building an equation sheet, just a separate sheet of paper where you put everything down and you list out what each variable is. Now, problems. This first one, a car accelerates from a red light at a rate of, okay, here's A, so while I'm going through this, I know this is A right over here, up a 45-meter long ramp, S, to get onto the interstate. How long, looking for time, does it take the car to accelerate up the ramp? So I drew out a quick picture over here. I'm going 45 meters. I have an acceleration of 3.9 meters per second. I'm calling everything that's going to the right to be positive and everything that's going to the left to be negative in this problem. So now I need to do an equation bank, or excuse me, a variable bank. Now, a big thing that I need to point out with this problem is my initial velocity is 0. I start out from rest. Now, that is not explicitly stated in this problem. A car accelerates from a red light. Now, at a red light, how fast is the car going in the very beginning? Notice in the picture I have U right here at the very beginning labeled as 0. So the car's initial velocity is 0. And you're going to find that happening a lot in problems where it's implied or it's stated using the word rest that it either starts from rest or it ends at rest. So either the initial or the final velocity is 0. So be careful. Make sure to read the problem well to figure out what's going on. I made my variable bank. Notice my displacement is positive because we are going to the right, and I call it to the right positive. Also, my acceleration is positive because we are speeding up to the right. So now I'm going to look at my variables that I have here in my variable bank, and I'm going to compare it to the equations I have up top, and I'm going to pick the right one. This is why a variable bank is so important. It makes choosing the right equation almost multiple choice. I already know this is going to be standard kinematics because this is just a simple acceleration problem. So I already know what I'm kind of going for, and I know the type of equations that I should be picking. It's going to be one of these three right here. And it's not basic velocity or acceleration because I've got a mix of acceleration and displacement, so that's no good. I am looking for time, so this equation over here is out. I need something that has time in it. It's one of these two. And I know initial velocity, and I know displacement also. So going through, this second equation must be the one I want to use. All right, so I wrote the equation down again, letter for letter, exactly as I had it on my equation sheet. Then I come over to the variable bank, and I just simply substitute in. S becomes 45 because that's what it is. U becomes 0 because that's what it is. T I don't know. That's the variable I'm looking for, so I leave it as T. 1/2 times A is 3.9, and then T squared. Notice I'm all in base units over here. So now I'm going to solve for T, and this is just simply algebra. All right, so in this step, notice that 0 times t is 0, so it completely goes away, and 1/2 times 3.9 is 1.95. So now I need to divide both sides by 1.95, trying to get that t squared all by itself. And that leaves me 23.0769, so forth, so on. You'd want to store that in your calculator. Equals t squared. I'm going to take the square root of both sides to undo the square. Undoing a square, the opposite of a square is a square root. And so now I'll end up with whatever t is. And time comes out to be 4.8 seconds. Notice here I have two significant figures, so I made sure to round my answer to significant figures there. All right, next problem. A deer steps out 65 meters in front of a car, traveling at, all right, so let's just, as I'm reading, I want to label, this is going to be my displacement. The car is already traveling 22.5 meters per second. That sounds like a U here, initial velocity, because it says it's traveling at this. Maximum deceleration, so I'm going to slow down, is this guy right here. This looks like A, but except I'm going to need to be careful about that. I'll show that here in a moment. Will they hit the deer? Now, this right here says comparison problem. Whenever it's a question of will this occur, you want to solve for a variable and then compare it to something. So I'm actually not going to use the 65 meters as my S. Instead, I know the deer is 65 meters in front of the car, and I want to compare. This is a comparison problem. So in my problem, if I solve for S, then I can compare it against how far the deer is in front of the car, 65 meters. So I drew a nice little picture over here. Notice what's happening. I'm calling to the right positive and back to the left negative. You have to pick a direction for positive and negative. Remember, vectors, they have a direction, and positive and negative qualifies as a direction. To the right positive, to the left negative. And since I am decelerating, you see that right over here, you notice that it's going to be going back to the left, opposite the direction of the initial velocity, which is to the right. Thus, I have to give my acceleration a negative sign. Deceleration, negative 4.8 meters per second squared. So be careful, just don't take it as 4.8. Check the direction that it's supposed to be going. The deer is 65 meters away. Now let's create ourselves a variable bank. All right, now I purposefully left the final velocity without anything in it. Most students, whenever they start doing this, they'll go, okay, acceleration negative 4.8 meters per second squared. Initial velocity might have been a little tough for them, but they figure it out. It's 22.5 meters per second. And S is what I'm looking for, and they go, but I don't have enough information. What you do, you know the final velocity. What's the purpose of the car? Well, the car is going to come to a stop. That's the purpose. If you're not going to hit the deer, you want to stop, final velocity of 0, before you get to the deer at S, 65 meters. So we're going to now solve for S to see if it's less than 65, great, we didn't hit the deer, or greater than or equal to 65, that stinks, we did hit the deer. Now we have our variable bank. Let's pick an equation. Notice I have A, U, V, and S, no time. So I'm going to want to pick the equation that does not have time in it. All right, so there's my equation, and I'm substituting in now to work the algebra. All right, so here in this step, I squared the 22.5, came out with 506.25, and subtracted it over. And then 2 times negative 4.8 gave me my 9.6. Next step is going to be to divide both sides by 9.6, so I can get S. My displacement, that's negative 9.6, because 2 times negative 4.8. So divide both sides by negative 9.6. And whenever I divide both sides by negative 9.6, note negative divided by a negative is a positive. That means we have a positive displacement, which makes sense, right? Because we're going to the right, which I call positive. So it better be a positive displacement, otherwise I did something wrong. So whenever I do that, I come out with 53 meters, meaning that no, we did not hit the deer.